My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I'm going to discuss interrupt handling. I'm going to begin by discussing interrupt handling at the hardware level, and then move on to features provided by the CPU, and finally, features of the operating system for handling interrupts. At the hardware level, devices are connected either via traces on the motherboard or via a shared messaging bus to the advanced programmable interrupt controller. The CPU checks for hardware interrupt signals from this controller after each user mode instruction is processed. So after each instruction is executed, running some particular program on the system, the CPU actually checks to see if there are any interrupts that need to be processed. If an interrupt signal is present, then a kernel routine is called by the CPU in order to handle this interrupt. The interrupt dispatch routine, if it's not implemented directly in hardware, is actually a compact and fast routine that could be implemented in the kernel, often coded in assembly language. It has to be that fast. The specific interrupt handler is always a kernel routine, or in the case of a microkernel, an external server routine, and this specific handler depends upon the type of interrupt received. These are typically coded in C. So once again, the fetch execute cycle, we check for an interrupt pending after each instruction is executed. If there is an interrupt pending, we escalate privilege to kernel mode, push the program counter onto the stack, in other words, save it so we can resume from that point in whatever program we're interrupting, and then go and handle the interrupt. We do this by loading the program counter, the new program counter, that is, from a fixed memory location provided to us by the interrupt vector table. The interrupt vector table gives us the address of all the different interrupt handlers. We need a separate handler for each type of interrupt. The clock requires different logic from the keyboard, for example. Other devices, such as, say, a webcam attached to your computer, needs different logic in order to process messages from it. So we have different interrupt handlers for each of these different devices. The table simply stores the addresses of each handler. And in our monolithic kernel case, the handlers are actually part of the kernel and are mapped into kernel memory space. The interrupt vector table consists of a list of each of these addresses for kernel handlers, and conceptually is mapped into both kernel memory and user memory so that it can be accessed quickly. And historically these started at address 0. However, the mappings are different depending on the architecture. On Intel-based systems, we have something called the interrupt descriptor table. And the IDT provides special instructions and data structures that are actually managed by the CPU itself so that interrupt handling can be as fast as possible and protection rings can be changed automatically. The IDT is simply a reserved block of RAM used by the CPU to jump quickly to a specific interrupt handler. This IDT is mapped into kernel space, which was originally beginning at address 0, but this mapping is actually flexible with modern CPUs and can be mapped into other parts of the memory space. The first 32 entries of the IDT are actually not used for interrupts per se, but they're actually used for CPU fault handlers, and then the interrupt vector table part of the data structure begins after the CPU fault handler table. When we actually go to handle interrupts, the handling occurs in the kernel, and this is done with two levels of interrupt handling, the fast interrupt handler and the slow interrupt handler. The fast interrupt handler is the piece of code that's invoked directly from the interrupt vector table whenever an interrupt occurs. This is the piece of code that the CPU is just going to jump to when an interrupt occurs. Fast handlers execute in real time, and they're called fast interrupt handlers because they need to be fast. The execution of one of these interrupt handlers needs to be short. If any large-scale data transfer needs to occur, say we need to get a lot of data from the device all at once, This operation is handled by having the fast interrupt handler enqueue something called a task into the operating system's task queue. Whenever all the fast interrupt handlers for all the different interrupts are done executing, the CPU will go and check the task queue and execute any tasks that are present there. The part of interrupt handling that goes into the task queue is called the slow interrupt handler, and it's called this because it's not executed immediately and it can be interrupted by other devices. So what happens if an interrupt request is received while we're still processing an interrupt from a previous request? Well, there's no problem if we're in the slow interrupt handler, because this processing is done in such a way that we can stop this processing and handle the new interrupt if necessary. But what happens if we're still running a fast interrupt handler? Well, the new interrupt handler could be executed before the first interrupt handler is finished, and this could cause some major problems, especially if we get a new interrupt from a device that's sharing the same interrupt line as the one that we're handling. So what we do is we make fast interrupt handling atomic. That is, we make it uninterruptible. On a single core system, this is as simple as disabling interrupts as long as we're running a fast interrupt handler. On multi-core systems, there are actual special machine instructions to facilitate atomic operations that are pegged to one CPU core. These atomic interrupt handling operations will run to completion without interruption by any other interrupt or any other request on the system. Thus, the longer an interrupt handler takes to run, the longer the system will be unresponsive to any new interrupts. So what happens if a fast interrupt handler is coded in such a way that it takes too long? Other devices might be requesting attention at the same time that this long-running interrupt handler is executing. Worse, the same device that generated the original interrupt might now have more data to deliver to the OS before all the previous data is completely received. This could cause hardware failures, buffer overflows, dropped data, dropped messages, all kinds of issues at the hardware level. However, inside the operating system, this could lead to something called an interrupt storm, which is really bad. An interrupt storm occurs whenever another interrupt is always waiting to be processed whenever a fast interrupt handler finishes its execution. That could occur either because the fast interrupt handler is too long and needs to be split into a fast and a slow handler. This can also occur if hardware has certain bugs that cause it to raise spurious interrupts. If the operating system is perpetually handling interrupts, it never runs any application code. Thus, it never appears to respond to any user inputs. The result of this situation is something called a live lock. The system is still running, it's still processing all these interrupts. However, it's not doing any useful work. Thus, to the user, the system appears to be frozen. And when an interrupt storm occurs and this live lock situation results, the typical way out of this problem involves judicious use of the power button. So, interrupt handling is an important concept in order to support multi-programming systems. And interrupt handling, when these interrupt messages come through from hardware, is divided into two types of handler so that we don't get the interrupt storm. The fast interrupt handler executes atomically without being interrupted by anything else, but it must be fast, must enter that interrupt handler, do some very short operations, and immediately exit that handler. If any long-running operations need to occur as a result of a device interrupt request, we need to handle those operations inside the slow interrupt handler.